Hello everyone and welcome to Lecture Today. So today we're going to be talking about improper integrals, continuing our discussion from the last lecture. The main idea here is I'll be going over some more examples and applications of type 1 improper integrals, and I'll also be discussing in a little bit more advanced terms type 2 improper integrals. But you'll recall here that I did in the last lecture a little bit of a review from Calculus 2 of the fundamental theorem of calculus and the idea of a definite integral. This is the fundamental theorem of calculus right here. And I basically discussed type 1 improper integrals of subtype 1 and 2. I did a couple examples of these. And remember that these improper integrals of type 1 are improper integrals over an infinitely sized domain. Subtype 1 is when the b endpoint goes to infinity. Subtype 2 is when the a endpoint goes to negative infinity. And subtype 3 is when both a and b go to negative and positive infinity. In today's lecture, I'm also going to be focusing on improper integrals of type 2. Subtype 1 is when f of x is discontinuous at the left endpoint, so type 2, subtype 1. Subtype 2 is when f of x is discontinuous at the right endpoint, or at b. Subtype 3 is when f of x is discontinuous at some midpoint, so some point c in between a and b. In a very similar manner to how improper integrals of type 1 subtype 3 are when both a and b go to positive infinity. Improper integrals of type 2 subtype 3 are when the function is discontinuous from both sides at some point interior to the domain of integration. So this is a very neat kind of summary and a very neat sort of connection between improper integrals of type 1 and type 2. They're both defined in a similar manner with similar ways of evaluating it using limits. So for the first example that we'll consider, I'm going to consider the improper integral of the function 1 over 1 plus x squared from negative infinity to positive infinity. And this is an improper integral of type 1 subtype 3. So both the endpoints are going to positive infinity. And we want to go through and figure out how to evaluate this. Now, in terms of what this function looks like, just for some visualization purposes, kind of draw two axes here. This function looks kind of like a bump. It's similar to what's called a bump function, where it very quickly kind of comes up from 0 and is kind of sharp here at the origin. So I'm going to redraw this, make it a little bit sharper, and then it quickly goes down to 0 as we go to positive infinity. So what we're interested in for this just mathematical example is the improper integral from negative infinity to positive infinity, which is actually the same thing as the area from negative infinity to positive infinity under this curve. And so you'll recall that in order to do this, we have to choose a value c. Any value c along the real number line should work. And we need to split this up into two separate parts. Specifically, we need to split this up into a positive part and a negative part, or an improper integral of type 1 plus an improper integral of type 2. And so I'm going to do this in general for a general value of c to show you that it can consistently be done for any value of c here that we want to choose. But an easier value of c to choose would probably be 0, because we can use some function simplification to get just one evaluation of an improper integral if we notice that 1 over 1 plus x squared is an even function. but I'm going to go through and do this in general just to show that it works. So I'm going to start with the second of these two improper integrals, the integral from c to positive infinity. And what's kind of neat here is that you can always think of an improper integral of type 3 as the sum of an improper integral of type 1 and an improper integral of type 2. Or sorry, subtype 1 and subtype 2. And it kind of gives a nice, neat consistency to evaluating these things. So we're going to split this up into the limit of, as the endpoint goes to infinity, of the definite integral from c to b, which is a proper definite integral. And just like before, we need to evaluate the integral first. You'll remember that the antiderivative of 1 over 1 plus x squared is the arctangent function, or the inverse tangent function. This is sometimes written, and it is written in the book this way, as tan to the power -1, or tan with a -1 in the exponent. I don't like writing it this way because it kind of causes confusion sometimes. If you put the power -1 in the exponent, sometimes people confuse this with the cotangent function, or 1 over tan. And arctan is not equal to 1 over tan. So I like calling it arctan to really emphasize that it's the inverse tangent function, or the inverse of the tangent function. But we took the antiderivative here, which gives us just arctan at the endpoints, so evaluated from b to c. And this is now, we're done with the first part here, which is doing our definite integral from c to b. We now need to evaluate this limit, the limit as b goes to infinity, of the arctangent function. And if you remember the inverse tangent function, you should remember that this limit is exactly pi over 2. So the answer for this integral that we get from c to infinity is pi over 2 minus arctangent of c. And this gives us the value of this first part of the integral that we're looking for. The next integral that we need, right, is the integral from -infinity to c of 1 over 1 plus x squared. I'm not going to go through this in a super lot of detail because I just went through and did the first improper integral, which is very, very similar to evaluate. So I'm going to let you go through and do this by yourself. It'd be good practice to do so. It uses the same function, the same antiderivative, so it shouldn't be too bad. But we should end up getting here pi over 2 plus arctangent of c when we go through and do that. And it's really a very similar calculation to the previous calculation, using the limit and the definition of improper integrals of type 1 subtype 2. But now we just need to put all of this together to compute the improper integral that we're looking for. And basically what that means is we have to add our two results together to get the final result, which is the integral from -infinity to positive infinity of this function itself. And we can see very clearly, almost without writing this down, but I'm going to write it down here just for good measure. We're going to get a very nice cancellation that occurs, and the value of this improper integral is going to be exactly equal to pi, because the plus arctangent of c from the first improper integral cancels with the minus arctangent of c from the second improper integral, and pi over 2 plus pi over 2 is just equal to pi. And what that means then is that the area under this function from -infinity to positive infinity is in fact pi, which is very cool and very, very neat, that we can go through and do calculations like this. It's also very, very useful. So in the next example, I'm not going to go through and do the integral out, but I want to point out a fundamental improper integral that occurs in many different areas, but is mainly related to what's called the standard normal distribution. So this is typically seen for the first time in a probability and statistics class, and the standard normal distribution is a probability distribution that governs and in many different ways is connected to pretty much every single phenomena that you could possibly think of, from the distribution of photons in physics to the distribution of grades in mathematics class. This function, the standard normal distribution function, looks like what's called kind of like a bump function, and it's very smooth. It kind of comes up, and there's a little bump here, and then it goes down. And the exact function is e to the negative x squared over 2. You can actually think of this as the standard normal distribution function that's kind of centered at 0 here, or at the mean of 0, and standard deviation or variance of 1. But this curve can be shifted, and it also can be stretched depending on what the actual parameters are, the statistical parameters are that you're using from your data set. But the idea here is that in probability theory, it's really important to know the area under a curve, and typical probability distribution functions, right, are valued on the entire real number line. So they go from negative infinity all the way to positive infinity. So being able to figure out the area of such a curve, such a distribution, is super important. The main reason that it's important is that you want to make sure that your probability distribution has an integral of 1 over its entire sample space, which essentially means that the probability of something happening in your sample space is 1. So the question here is, how do we determine the integral of this function from negative infinity to positive infinity? What is this value? And I will give you what the exact value is. Turns out that it's relatively, it's a little bit difficult, but we can go through and show that it's the square root of 2 pi. Now, I won't be showing this in this class because in order to do this, it requires some multivariable calculus. Specifically, you're going to have to use double integration in polar coordinates. So we will introduce polar coordinates later on in this class, but you need to wait a little bit longer to kind of see this calculation done out. But the idea is that it's very neat and very fundamental to pretty much every area of modern physics and modern, not just physics, but modern really probability and statistics. The main reason that you would want to normalize a probability distribution is that you need the integral of it to integrate to 1. So you need to multiply by the appropriate constant. In this case, it'll be 1 over the square root of 2 pi to get out the correct probability density function. But I think that's enough for this example. I can definitely talk about it more if you have any questions in class. So the main part of the lecture today, I want to spend discussing improper integrals of type 2 and what the similarities are to improper integrals of type 1, and also the differences. So like how kind of they differ. So I drew a couple examples of these for subtype 1, subtype 2, and subtype 3 here, and I'll discuss how to go through and evaluate these. And like I said before, it's going to be very similar to improper integrals of type 1. We're still getting an infinitely sized object that we're integrating over, but in this case, the domain is not actually the infinitely sized object, it's the range is infinite. So this is an example function here, y equals f of x. for an improper integral of type 2 subtype 1. This is where the function has a discontinuity, goes to positive infinity at the left boundary point a, right here. So the type 2 subtype 1 is where there's a discontinuity at a. So if I were to write down the integral from a to b of the function f of x, this would in fact be an improper integral, and the correct way to evaluate this has to be taking the limit as, we'll say, c approaches a from the positive, from the right, of the integral from c to b of f of x dx. So this is the correct way to evaluate an improper integral of type 2 subtype 1. Just essentially using a limit, and what we're doing here when we calculate this improper integral is we're saying, well, fix c. So like c can be like right here, say, and so the improper integral of the function from c to b can definitely be evaluated because the function is defined at c, and it's defined for all of these points as well. So what this is saying is solve for this integral from c to b, and then whatever you get for your result, just take the limit of that as c goes to a and f goes to the bad point, which is the point of discontinuity, the boundary. Just like for improper integrals of type 1, if the limit exists, we say that this converges. And it diverges if the limit does not exist. So this is a neat similarity. Improper integral of type 2 subtype 2 is right here. This is type 2 subtype 2. Is pretty much the same thing, or very similar to subtype 1, only for type 2 we have a discontinuity at the upper bound, at b. So we say that f of x is discontinuous at b, whereas for type A, or type 1, f of x is discontinuous at the left bounded point. So type 2 subtype 2 is where f of x, the function, is discontinuous at b, and again we have to define this as now the limit as c goes to b of the integral from c to b, or a to c of f of x dx. If the limit exists, the improper integral diverges. If it does not exist, or d and e, the improper integral, other way around, sorry. If the limit exists, it converges, and if the limit does not exist, it diverges. Well, this makes a lot of sense. And again, it's very similar to what we're doing for improper integrals of type 1. We're just kind of doing it in a slightly different way because we have a different type of infinite set here. But again, we're saying we take the integral from a to c, which is perfectly fine, right? This is a definite integral. It's a proper definite integral from a to c for any value of c that's away from the discontinuity, we're getting the total accumulation of the function on that interval from a to c. Then once we have that value, we take the limit as c approaches the bad point of f. And you'd be surprised, there are many, many functions for which this value does exist, and we can talk about the accumulation of the function under even a function that's discontinuous and contains a discontinuity. It doesn't always converge, which is why we have a difference between convergence and divergence. There are many other functions for which it diverges, but it's very, very important to understand the difference. And you're probably wondering about subtype 3, and just like the other two examples, subtype 3 is defined very, very similar to subtype 1, which is awesome. This is type II Subtype 3. This is where we have a discontinuity in the middle of our domain from A to B. So we have improper integral on the left and an improper integral on the right. So what we can do is utilize what we've just done, which is define, and I guess what I'll do is instead of C here, I'll put X star. So just to not confuse with the C before. I also used X star in my last lecture. So if we have a discontinuity here at, say, this X star, in order to find the improper integral from A to B, the most natural way of doing this is by splitting it into two parts, the improper integral from A to X star, which is an improper integral of type 2, subtype 2, because there's a discontinuity on the interval from A to X star on the right. And to add to that, the improper integral from X star to B. Because this is an improper integral from X star to B of type 1, or so I should say it's type 2 subtype 1, right? It has a discontinuity on the left of the interval. But this is pretty much it for improper integrals of type 2. So this is what we're always going to have to deal with when we're going through and evaluating them. We determine what type of improper integral we're evaluating, and then we go through and figure out what all of the subcomponents are. The more complicated ones are type 2, subtype 3, but you can see very clearly that these always will break down into improper integrals of subtype 2, either 1 or 2. So you can just add these together, figure these out, and then add them together. So let's do a relatively straightforward example. We'll do the integral from 0 to 1 of 1 over the square root of x. And we know that this is a function with a discontinuity at x equals 0. Because 1 over 0 is undefined. So the function 1 over the square root of x looks like this. And what we're looking for is essentially if the accumulation of this function, or because it's positive, the area under this curve is finite or not. And if it is it possible to evaluate the value, or its value? So for classification purposes, we can see that this is an improper integral of type 2 subtype 1 because it has a discontinuity at x equals 0. And so we can directly evaluate this by taking the limit as c goes to 0 from the positive. Oops, and I just want to make sure that I put this here. Yes, I put c goes to a from the positive here. This should be c goes to b from the negative. I know that it doesn't maybe seem super important, but it is very, very important because these types depend on the direction of approach of the point. So it's the limit as c goes to 0 of the integral from c to 1 over x to the square root of x dx. So just like before, we can evaluate this by kind of separating these two processes. We do the integral first, and 1 over the square root of x is the same thing as 1 over x to the 1/2, which is the same thing as x to the negative 1/2. So you'll remember that the antiderivative of x to the negative 1/2 is going to be 1 over negative 1/2 plus 1 to the times x to the negative 1/2 plus 1 plus c. Or this is going to be equal to, well, 1 plus negative 1/2 is just 1/2. So 1 divided by 1/2 is 2. So it'll be 2x to the 1/2 plus c. Or that's 2 times the square root of x. And we have to remember to evaluate this at the upper bound of 1 and the lower bound of c. So we can pull out the constant 2. This becomes the limit as c goes to 0 from the positive of square root of 1 minus the square root of c. And this limit is just 1 minus 0. So the value of our improper integral of type 2 subtype 1 is exactly 2. Moreover, this value of 2 is exactly the correct value of the area under the curve from 0 to 1, even though the function 1 over the square root of x is undefined at the origin, at the point 0. So this is a very neat result here, and I think very clearly shows how we go through and calculate such improper integrals. So let's do one more example problem, just to make sure that we have the basics of evaluation down. So this one, we'll go through and do the integral from negative 1 to 1 of 1 over x to the 2/3 dx. And we immediately recognize that our function, our f of x here, right, it has a discontinuity at the point 0. So 1 over x to the 2/3 is discontinuous at x equals 0, or x star equals 0. And so therefore, this is an improper integral of type 2 subtype 3. And so we have to go through and split this up into two separate improper integrals, one from negative 1 to 0, and one from 0 to 1. Both of these antiderivatives are of the function 1 over x to the 2/3, or x to the negative 2/3, the antiderivative of which is going to be 1 over negative 2/3 plus 1 times x to the negative 2/3 plus 1. So this is going to be equal to plus c. 3 times x to the 1/3 plus c. So the first part of this integral, we'll look at this integral right here, the improper integral from 0 to 1 of 1 over x to the 2/3, which is the limit as x goes to 0 from the right. Oh, I also want to just, we have that in the limit right here, which is good. This is of the antiderivative of this expression, which is 3 times x to the 1/3. This is evaluated at the upper bound, the lower bound c, and the upper bound of 1. So this is the limit as c goes to 0 from positive. It'll be 3 times 1 to the 1/3 minus 3 times c to the 1/3, or 3 and then in pretty much the exact same way, we can go through and evaluate the integral from -1 to 0, which is going to be equal to the limit as c goes to 0 from the negative of the integral from -1 to c of 1 over x to 2/3 dx. And for the exact same reason, the antiderivative of 1 over x to the 2/3 is 3 times x to the 1/3 from c to -1. Which is just the limit as c goes to 0 from the left-hand side of 3 times c to the 1/3 minus 3 times -1 to the 1/3, which is just -1. This is equal to 0. This limit is 0. This limit is there's negative times -1, which is just times 3, which is just equal to 3. So the value of the answer that we're looking for is exactly 3 plus 3, or 6. And this is the final answer to the problem. So these are just two relatively straightforward examples of how we can use our integration techniques to go through and evaluate improper integrals of type 2. This will conclude today's lecture. I think I've shown a number of different good examples and really explained what improper integrals of type 2 are. The next lecture video, I'll consider discussing two separate convergence theorems, because sometimes knowing how to evaluate a given improper integral is just it's just not possible. The value that you get for the antiderivative of the actual function that you're integrating could be very complicated or too complicated, and it's easier a lot of the time to test for convergence or divergence without even evaluating the value of the actual integral itself. So we'll be talking about these two convergence theorems called the direct comparison theorem and the limit comparison theorem in the next lecture video.